The elements of group 1, or alkali metals, are a family of very reactive elements, which have a great tendency to lose their outermost electron to four cations with charge 1+, to acquire the more stable electronic configuration of a noble gas. Because of the great tendency to lose electron, alkali metals are very good reducing agents, and they are capable to reduce water, producing hydrogen gas as a product of the reaction. The reaction becomes increasingly violent on the standing the group, as long as the metal increases its tendency to lose electrons with more negative reduction potential. This fact is rather surprising if we examine the reduction potential of lithium, which is the most negative in the group, but on the contrary is the less reactive metal. The reason of this behavior is because the reaction is controlled by kinetics factors. Let's examine the reaction of the three first metals in the group: lithium, sodium, potassium with water. As we can see, all of them are introduced in a liter container with oil in order to prevent oxidation with the atmosphere. Let's start the demonstration with lithium. Lithium, as you can see, it's got a grayish appearance due to the oxide coating. But if we remove the surface with a knife, we see the silvery shiny appearance of the metal. Now I'm going to cut a small clean piece of lithium and put it in a crystallizer with water. And as you can see, it's reacting, bubbling and fizzing. Now, if I add some drops of an acid-base indicator called phenolphthalein, which is colorless in acid solution and turns pink for basic solution, we see as the solution turns immediately pink. This is because in this reaction lithium hydroxide has been produced, which is a basic compound. Let's see the same reaction now with sodium. Now, if you look at it closely, there is a kind of white coating on the metal. And again, if we cut it with a knife, we see that sodium is a soft metal and it's easier to cut than for lithium. And again, we can observe its shiny appearance. In this case, the metal oxidizes faster than lithium for the oxidation with the atmosphere. Let's drop it in the crystallizer with water, but this time with phenolphthalein in the crystallizer before. We will see how the reaction proceeds much faster and the solution turns pink quickly. As you can see, a flame comes out from the molten metal that is moving, floating around in water, not only because it's less dense than water, but also by the effect of the hydrogen that is being produced. Finally, we are going to observe the reaction of potassium. The reaction of potassium with water is a more reactive reaction, it's a more explosive reaction, as you can observe in the following sequence. Let's scratch the gray surface, although as we can observe, its turn is really faster. We see that the reaction with water is really faster and we get the pink color again. Now we're going to do some flame tests with common compounds of lithium, sodium and potassium, which is a usual analytic procedure employed in chemistry to identify elements, in this case alkali metal ions. For the demonstration, we have prepared a spatula pin to a piece of cork, 3 samples of lithium, sodium and potassium chloride, and a beaker with water to rinse between the different experiments to avoid the contamination as we go from one test to another one. The procedure is pretty simple. It consists on taking a little sample of these salts and then I'll place it over the flame. We can see in the case of lithium ion its characteristic beautiful crimson color. Now I'm going to rinse the wire in order to remove some residue of the lithium salt that can be on it. And we can keep on doing the demonstration with sodium. Now we can see the typical bright yellow color, well, what is typical for sodium. After rising again, I'm going to finish with potassium, and we can observe its characteristic lilac color. So we have seen how from these solid salts of the alkali metals, we are able to observe on the flame some beautiful color characteristic for each alkali metals. As we move down in the group, the ionization energy decreases and the outermost electron in each succeeding element absorbs more and more energy and it gets more higher level energy. When the excited electron returns to the ground state, the amount of energy and the frequency of the light emitted go on increasing as we move down in the group. That's exactly what we have seen in this experiment. The color of the flame shows a regular shift from the red to the violet region in the visible spectrum.